Dear students, welcome back. In this class we will discuss the existence of primitive root mod 2p power alpha. So in previous class we were discussing g is a primitive root mod p, then g is a primitive root mod p square only if g power p minus 1 is in congruence 1 mod p square. Now here the conditions of existence of primitive root or the primitive existence of primitive root mod 2p power alpha. So the theorem says that if g be a primitive root or let p be an odd prime, p is an odd prime and alpha greater than or equals 1, then there exists an odd primitive root g mod p power alpha, odd primitive root g mod p power alpha. Each such g is also a primitive root mod 2p power alpha. P is an odd prime, alpha greater than or equals 1. Then there exists an odd primitive root g mod p power alpha. Then for each such a g is also a primitive root mod 2p power alpha. How? So the proof is g be a primitive root mod p power alpha. Primitive root mod p power alpha. G be a primitive root mod p power alpha means g power phi of p power alpha congruence to 1 mod p power alpha. Okay, g power phi of p power alpha congruence to 1 mod p power alpha. So, what about g plus p power alpha? Consider g plus p power alpha all power phi of p power alpha. G plus p power alpha all power phi of p power alpha. So, by binomial expansion, it is g power phi of p power alpha plus phi of p power alpha c1. Phi of p power alpha c1 means it is phi of p power alpha into g power phi of p power alpha minus 1, g power phi of p power alpha minus 1 plus it is minus 1 into phi of p power s into p power alpha plus etc. Okay. So that is g power phi of p power alpha plus phi of p power alpha into g power phi of p power alpha minus 1. It is some k. So k into p power alpha. Okay. That means g plus p power alpha all power phi of p power alpha is congruence to g power phi of p power alpha mod p power alpha. Okay, all the terms except the first consists of the term p power alpha. So g plus p power alpha all power phi of p power alpha is congruence to g power phi of p power alpha mod p power alpha. But actually what about g power phi of p power alpha? That is nothing but from equation 1 it is g power phi of p power alpha is congruence to 1 mod p power alpha. So this implies g plus p power alpha all power phi of p power alpha is congruence to 1 mod p power alpha. Clear? So what's your conclusion? That means g plus p power alpha is also a primitive root mod p power alpha by definition. So g plus p power alpha is also a primitive root mod p power alpha. Okay. So we know that. So here when g is a primitive root mod p power alpha, here we show that g plus p power alpha is also a primitive root mod p power alpha. Agree? Now listen, since p is odd, when p is odd, so what about p power alpha? P power alpha is also odd. Agree? Now, if g is even, then g plus p power alpha is odd. Since p power alpha is odd, If G is even, G plus P power alpha is odd. Then either G or G plus P power alpha is odd. Either G is odd, when G is odd, so G is a primitive root of mod P power alpha. When G is even, then G plus P power alpha is odd, also G plus P power alpha is also a primitive root of mod P power alpha. Agreed? That means odd primitive root mod P power alpha always exists. If G be a primitive root, if G is odd, then G be a primitive root of mod P power alpha. If G is even, then G plus P power alpha is odd. But here we see that G plus P power alpha is also a primitive root of mod P power alpha. So here we conclude that odd primitive root of mod P power alpha always exists. Okay. Now let G be an odd primitive root of mod P power alpha. Now we have to show that this G is also there exists or each for such G there is a primitive root of mod P power 2 alpha. That is what we reduce. Agreed? So far, since G be a primitive root of mod P power alpha, let F be the exponent of G mod 2 P power alpha. That is, F is exponent of G mod 2 P power alpha. F is exponent of G mod 2 P power alpha means, by definition, it is G power F congruence to 1 mod 2 P power alpha. Okay. Now we have to show that to show this G be the primitive root mod 2 P power alpha, it is enough to show that this F equals or exponent of G mod 2 P power alpha equals phi of 2 P power alpha by definition of primitive roots. Okay. So to prove G being a primitive root mod 2 P power alpha, it is enough to show that this F equals phi of 2 P power alpha. Okay. To prove F equals phi of 2 P power alpha, it is enough to show that F divides phi of 2 P power alpha and also phi of 2 P power alpha divides F. That is what we require here. Okay. Now, since F is exponential of G mod 2 P power alpha, then F divides then clearly F divides phi of 2 P power alpha. Clear? F divides phi of 2 P power alpha. But what is phi of 2 P power alpha? Phi of 2 P power alpha is, since phi is multiplicative, it is phi of 2 into phi of P power alpha. What is phi? Phi is an Euler phi function. It is multiplicative. So it is phi of 2 into phi of P power alpha. What is phi of 2? Phi of 2 is 1. So phi of 2 P power alpha equals phi of P power alpha. Okay. Therefore, F divides phi of P power alpha gives F divides phi of P power alpha. Okay. Yes. Since G star, let G star equals G star is congruence to 1 mod P power alpha. G star congruence to 1 mod 2 P power alpha. Let G star congruence to 1 mod 2 P power alpha. That means 2 P power alpha divides G star minus 1. Okay. So 2 P power alpha divides G star minus 1 means surely this P power alpha divides G star minus 1. Okay. That means G star congruence to 1 mod P power alpha. G star congruence to 1 mod P power alpha. What is G? Since G be a primitive root mod phi of, since G be a primitive root mod P power alpha, we have phi of P power alpha strictly less than F. Agreed? That means phi of P power alpha strictly less than F means phi of P power alpha must divide F. Okay. So here phi of P power alpha divides F and F divides phi of P power alpha. That combinedly gives F equals phi of P power alpha. But what is phi of P power alpha? Equals phi of 2 P power alpha. So finally F equals phi of 2 P power alpha. f equals phi of 2p power alpha means f be the, what is f? Exponent of g mod 2p power alpha. That is same as phi of 2p power alpha means g be a primitive root mod 2 power alpha. So this is the existence of primitive root mod 2 power alpha, 2p power alpha. Okay. Right. Now consider the non-existence of primitive roots in the remaining cases. So the non-existence of primitive root in the remaining cases means, so the theorem states that for alpha greater than or equals 1, or instead of alpha, suppose m, take them for m greater than or equals 1, where m is not of the form, m is not of the form 1, 2, 4, p power alpha or p power 2 alpha. Why? Because all of these cases, when m equals 1 or 2 or 4 or p power alpha or p power 2 alpha, we already proved that the primitive root exists for this here. Okay, existence of primitive root mod 1, existence of primitive root mod 2, existence of primitive root mod 4, existence of primitive root mod p power alpha, and existence of primitive root mod p power 2 alpha. The last case. Already these cases are finished. Now, for m greater than or equals 1 and m is not of the form 1, 2, 4 or p power alpha or p power 2 power alpha, where p be an odd prime, then for any a with a and m are relatively prime, then a power phi of m by 2 is congruent to 1 mod m. Why this is so? Means when we already proved that for alpha greater than or equals 1, we already proved a result when alpha greater than or equals 1, a and m are relatively prime, x be an odd integer, then alpha greater than or equals 3, we have x power phi of 2 power alpha by 2 is congruent 1 mod 2 power alpha, means there does not exist a primitive root mod. Okay, so to prove that non-existence of primitive root mod in other cases means for m greater than or equals 1 and m is not of the form 1, 2, 4, p square, p power alpha or p power 2 alpha, with a and m are relatively prime, then a power phi of m by 2 is congruent to 1 mod m means there is no primitive root mod m. If we prove for any a with a and m are relatively prime which satisfies this condition, a power phi of m by 2 is congruent to 1 mod m, then we conclude that there does not exist a primitive root mod m. Okay, so that is the case. Let me discuss. So we have already shown that there are no primitive root mod 2 power alpha if alpha greater than or equals 3. That is the theorem already proved. When alpha greater than or equals 3, x be an integer, then x power phi of 2 power alpha by 2 is congruent to 1 mod, this case, x power phi of 2 power alpha by 2 congruent to 1 mod 2 power alpha, then there does not exist a primitive root mod 2 power alpha. The theorem already finished. So, now we suppose that m has the factorization. If m has the factorization, m equals 2 power alpha into p1 power alpha 1 into p2 power alpha 2 into etc. into ps power alpha s. Okay, alpha s, where p's are odd primes pi's are, or each of this pi odd prime, comma, alpha. What is alpha? Alpha greater than or equal 0, alpha greater than or equal 0, and s greater than or equals 1. M equals 2 power alpha, p1 power alpha 1, p2 power alpha 2, etc. ps power alpha s, where pa is an order prime, alpha greater than or equals 0, and s greater than or equals 1. So this is the factorization of m. Clear? Since m is not of the form, that is our hypothesis. M is not of the form 1, 2, 4, p power alpha or p power 2 alpha. Since m is not of the form this one, when alpha greater than or equals to, what happens? When alpha greater than or equals to, then if s equals 1. Why? If s equals 1 and alpha less than 2, what happens? If s equals 1 means m equals 2 power alpha into p1 power alpha. Okay, if alpha s equals 1, so this m is 2 power alpha into p1 power alpha. Okay, and when s alpha greater than or equals 2, since m is not of the form m but f, so when alpha s equals 1, what is m? M equals 2 power alpha into p1 power alpha. If alpha equals 1 here, what is of the form? Alpha is 1, m is 2 into p power alpha. M is p into 2 into p power alpha. We already proved that when p power alpha is a primitive root, then 2p power alpha is also a primitive root. Okay. When alpha equals 2, it is 2 power 4 into p1 power alpha 1. So 2 power 4, 2 square and so on. So since m is not of the form 1 to 4 p power alpha and p power 2 alpha, then if alpha greater than or equals to, if s equals 1, and s greater than or equals to, then alpha equals 0 or 1. Alpha is 0 or 1. Okay. Why? Because the choice of m is not of the form 1, 2, 4 p square, p power alpha or p power 2 alpha. Clear? But what is m? M has a factorization 2 power alpha into that one. So what is phi of m? Phi of m equals, since phi of 2 power alpha into p1 power alpha 1 into etc. into ps power alpha, yes, but phi is multiplicative. So it is phi of 2 power alpha into phi of p1 power alpha 1 into etc. into phi of ps power alpha is. Clear? That a and m are relatively prime, that is already given. Now we wish to prove that a power phi of m by 2 congruence to 1 mod. That is what we require here. Let G be a primitive root. Let G be a primitive root mod p1 power alpha. G be a primitive root mod p1 power alpha 1 means, come on, G power phi of p1 power alpha 1 is congruence to, that gives G power phi of p1 power alpha 1 congruence to 1 mod p1 power alpha. That's the choice of G. And let K, choose K such that there exists K such that a power K is congruence to, A is congruence to, not a power K. Choose K such that A congruence to G power K mod P1 power alpha. Okay. G be a primitive root mod P1 power alpha 1. That means G power phi 1 power G power phi of P1 power alpha 1 congruence to 1 mod P1 power alpha. And you can choose K such that A congruence to G power K mod P1 power alpha. Clear? Therefore, what about A power phi of m by 2? A power phi of m by 2 is congruence to G power K into phi of m by 2 mod p1 power alpha. Okay. But what is k into phi m by 2? Phi m is this one. So k into phi m by 2 equals k into phi of m means phi of 2 power alpha into phi of p2 power alpha 2. You can arrange this way, etc. into phi of ps power alpha s all by 2 into what remains there? Phi 1 p1 power alpha. Okay. K into phi m by 2 is k into phi of 2 power alpha, phi of p2 power alpha 2, etc. phi of ps power alpha s by 2 into phi 1 p1 power alpha. So what about this one? This is some t. So it is t into it is phi of p1 power alpha. Okay, where t equals this one. K into phi of 2 power alpha into phi of p2 power alpha 2 into etc. Phi of ps power alpha s by 2. Clear? Then, therefore, a power phi of m by 2 is congruent to g power, instead of k into phi of m by 2, it is t into phi of p1 power alpha 1 mod p1 power alpha. A power phi of m by 2 congruent to g power t into phi of p1 power alpha 1 mod p1 power alpha. Okay. Now, to prove t is an integer, that is in the next class. Now, this remains to show this t is an integer. Okay, that is we will discuss in next class. Thank you.